Hello, my name is Mara Swift. I am from Audubon, Pennsylvania, where I attend Methacton High School. I am part of Team Opportunity. Our team is competing in the Rapidly Prototype Tool Challenge, and we have designed a multi-purpose tool called the Every Need Transformable Tool, or ENT. I am here to present the overview of the ENT, but first I will discuss the brainstorming that led to our final design. The length and volume requirements of the challenge eliminated large, bulky tools from our consideration, and instead we focused on hand tools. To make up for the small size of the tool, and to make the best use of all the advantages of 3D printing, we wanted to create a tool whose parts could be built and recycled as needed. One important concern for us during the brainstorming process was making the tool easy for astronauts to use in a spacesuit. We had considered designing a shovel attachment that could be used to collect surface samples, but decided against it because it would be hard for astronauts to bend over to use the tool. In choosing our final design, the most important consideration is tools. We thought of the kinds of tools that are important for building and repairing equipment in space, and that led us to select a Phillips and flathead screwdriver to attach to our tool. We also considered what tools would not be needed in space. For instance, you don't normally think of astronauts using hammers and nails in space, so the ENT does not have a hammer attachment. Now we will move on to an overview of the ENT and its parts. The ENT is made up of 3 parts, the handle and 2 attachments. The handle is a cylinder 12 centimeters long and 1 centimeter in diameter, and it has a groove on one end to accept the attachments. There are 2 screwdriver attachment heads, one Phillips and one flathead, and each has a width of 9 millimeters. The Phillips head has a length of 2 centimeters, and the flathead has a length of 2.2 centimeters, so the total length of the tool at any time is no more than 14.2 centimeters. Now that we have gone over the brainstorming and overview of the tool, I'll send it over to Ashley to talk about designing the computer model.
Hello, my name is Ashley and I'm from Graham, Washington, and I'm homeschooled. I'm part of Team Opportunity. Our team is competing in the Rapidly Prototyped Tool Challenge. Our tool is named ENT, which is short for Every Need Transformable Tool. I'm going to discuss the creation of our tool using SketchUp and show that our tool fits the RaPTC requirement. Our tool consists of a handle and various attachments. The 2 attachments we have modeled are a Phillips head screwdriver and a flathead screwdriver, but virtually any tool can be modeled and printed so that it fits into the handle. The idea behind the attachments is that you can recycle the material when you're finished with an attachment and reuse it for something else, but you don't have to recycle the entire tool. RaPTC requires the tool to be under 20 centimeters long and less than 25 centimeters cubed in volume. The volume of a cylinder is pi r squared times height. Our handle has an 0.5 centimeter radius and is 12 centimeters tall, so the volume is pi times 0.5 squared times 12, or 9.425 centimeters cubed. Since our attachments are no wider than 1 centimeter and no longer than 1 centimeter, they could fit into a cylinder of volume pi times 0.5 squared times 1, or 0.785 centimeters cubed. Therefore, our tool is less than 10.21 centimeters cubed, which is less than the maximum of 25 centimeters cubed. Because of this, our tool is within the RaPTC requirements.
Hello, my name is Haley Hecox. I am from Greenbrier, Arkansas, where I attend Greenbrier High School. I am a part of Team Opportunity, and we are involved in NASA's Rapidly Prototype Tool Challenge. Our tool is named ENTT, which stands for Every Need Transformable Tool. I am here to discuss the materials and cost involved in creating our tool. I will also be presenting a live model of our tool and all of its corresponding pieces. So first I would like to discuss the materials involved in creating our tool. Our tool is created using the typical extrusion-based technology of 3D printing. The thermoplastic in which we employed is ABS, or acrylonitrile butadiene styrene. ABS's strength, flexibility, machinability, and high resistance to temperatures makes it a preferred plastic for engineers or for professional applications such as these. So, before I present the model of our tool, I would like to say a huge thank you to Greenbrier High School and its East program for allowing our team to use their MakerBot in order to create this 3D model. The MakerBot, to which we use to create our 3D model, uses an alternative to ABS, which is a corn-based PLA plastic. This is our handle. It is approximately 12 centimeters long and 1 centimeter wide. It has an opening at this end where the attachment side is, and our handle took approximately 15 minutes to print on the MakerBot. This is our Phillips head attachment. It is approximately 9/10 centimeters in width and 2 centimeters in length, and it took approximately 5 minutes to print on the MakerBot. This is our flat head attachment. It is approximately 9/10 of a centimeter in width and 2.2 centimeters in length. It also took approximately 5 minutes to create on the MakerBot. Now I will demonstrate how the attachments are put into place. Here's the handle, and then here's our flathead attachment. And it easily slides right out. And then this is our Phillips head attachment. And it easily slides out as well. However, it does not slide out too easily. It stays within and does not fall out. Next, I would like to discuss a very important concept: recyclability. Astronauts on long duration type missions could recycle tools as they are needed, saving space, volume, and resources. ABS has the capability to be recycled. So an idea that Team Opportunity developed in order to put this property into use would be the idea of recycling on location. For example, if our tool was no longer applicable or needed, an astronaut could then dispose of this tool into a small robot. The small robot would then grind up the tool and recycle the ABS. The ABS could then be placed back into a 3D printer on site. So now I'd like to discuss the cost involved in order to create our tool. According to MakerBot, PLA costs approximately 5 cents per gram. This varies depending on the specific PLA material in the version of the MakerBot. Using this generalized cost, PLA approximately costs $22.68 for 1 pound of PLA material. It must also be noted that generally PLA runs $8 to $10 cheaper than ABS for a 2.2 pound supply. So, correctly doing the math, 2.2 pounds of ABS cost roughly $59.90. Now, converting back to grams, ABS cost approximately 6 cents per gram. Our tool in total weighs 5.742 grams, and if our math is correct, our tool's projected cost in order to create would be 34 cents.